hardest problems as we go along. So the simple problem. So we have to find the Lorentz series expansion of this following function in the given region. So this is the region. So this region covers all the complex plane except the point z equal to 1. Okay, so we'll find the Lorentz series of the given function in the given region. So that is the whole complex plane excluding precisely the point z equal to 1. So you see in this region, so let us look at this function. So I hope you can follow the mouse pointer. So the numerator, which is e to the power minus z, so it is already an entire function, so it is everywhere analytic. And the denominator, so it has 0 at z equal to 1. So that is why the function fz, it is non-analytic precisely at z equal to 1. So except that z equal to 1 point, it is analytic everywhere. So when it is so we are expanding around the point of non-analyticity of this function. So that is why we expect, and we are expressing as a power series around the point z equal to 1. So that is the point of singularity. So when we express this function as a power series of z minus 1, so we expect negative powers to occur because this function is divergent at z equal to 1. So we'll see, so when we expand around z equal to 1, so negative power of z minus 1 will happen. So as usual, so let put t equal to z minus 1, and this is simple substitution. So we get e to the power minus t minus 1 divided by t square. So now we'll expand this e to the power minus t function. So of course this is the simple power series, we're all familiar with that. So this is just simple expansion, and the expansion for e to the power minus t is valid everywhere. But I have written this constraint mod t greater than 0 precisely for this factor of 1 by t square. So because of this factor of 1 by t square, I have written mod t greater than 0 here. Otherwise, as you know, e to the power minus t has a series expansion. This is the series expansion for e to the power minus t. This is valid for any value of t. So now simple manipulation. So I just carry this t square t to the power minus 2 factor inside this summation to get this term, and then finally I substitute t equal to z minus 1 to get the final answer. So this is the Lorentz expansion around z equal to 1. So as we expected, so we see that there occurs two negative powers of z minus 1. See, so the summation is from n equal to 0 to infinity. So if we put n equal to 0 here, so the power is z minus 1 to the power minus 2. And similarly, if we put n equal to 1, so we will get z minus 1 to the power minus 1. So of course, so as we can see from here, z equal to 1 is a second order pole. So the power series expansion captures this behavior. So we have, so what do we have? So we have z minus 1 to the power minus 2. So that is the maximum negative power of z minus 1. So that is why it is a second order pole. So yeah, that's that. That concludes this first problem. So now we move on to the second one. So another Lorentz series function. Yeah. So another Lorentz series expansion. So we have been given a rational function. So numerator and denominator both are polynomials, and we have to expand this function in a Lorentz series in the region, in this region. So mod z is less than 6 but greater than 1. So this is an, what do you say? This is an annulus. Sorry. I think yeah. So how to tackle this kind of problem? So if we are given some rational function, so we usually express them first as sum of terms, right? So like we express them as sum of terms which have some numerator or denominator as polynomials of 0 degree. So like this function, so this function has this following this summation expansion. So we can find these coefficients easily. You can check that the sum of these two terms give this function. So now we'll expand these two fractions in two different power series centered around z equal to 0. So yeah, please be careful that we have to expand around z equal to 0. So because our region is this, which is centered around z equal to 0. Okay. So the power series should also be centered around z equal to 0. So let us look at this first term. So what do we have in this given region? We already have 1 by mod z less than 1. So the power series, so what do we know? The power series converges when the sums goes to 0 as n tends to infinity. So that is one of the criteria for convergence. So here we have to compare these things. So 1 by mod z less than 1. So like now it's easy to perform. So we have earlier performed this kind of analysis. So 1 by z minus 1. So I have extracted the factor of z to write it as a function of 1 by z. Simple. Now we'll do the binomial expansion for negative powers. Clearly this is the series 1 minus 1 by z to the power minus 1 is this thing. Okay, yeah. So clearly we all recognize this series to be this one, 1 by z to the power n. Okay, and then I put the outside 1 by z factor inside. So that is why we get this final answer as this series. So 1 by z minus 1 is represented by this power series in this region. So mod z greater than 1. So So yeah, one thing is that it may seem like we are getting a negative power of z. So you may naively conclude that we are getting a we are only getting negative powers of z. There is no positive power in this series. So you are clearly this is visible, but we have to keep in mind that we are expanding as a function of 1 by z. Okay, so this is the power series. So if we treat that as a power series of 1 by z like this thing, so clearly only positive powers of 1 by z occurs. So that is why as a function of 1 by z, this function is analytic in the given region. So, and since it is analytic as a function of 1 by z, so it is analytic also as a function of z. So please don't be confused with the occurrence of negative powers of z, because in this given region the point 0 is already excluded. You see, this is the annulus, so 0 is already excluded. So no problem with the negative powers. Okay, then we have calculated the first series, then we move on to the second one. So that is 1 by z plus 6. Okay. And of course, in the given region, we have mod z by 6 less than 1. So because our region is this one. So again, so due to convergence issue, we have to express this function as a power series of z by 6, because z by 6 has modulus less than 1. So how to do that? So first take a factor of 6 out, and then what remains is 1 plus z by 6 to the power minus 1. Then expand that in the binomial series with negative power, and we easily get this expansion. So minus 1 to the power n, z by 6 whole to the power n. So finally putting all these pieces together, so this is just substitution. So that was minus 2 by 7 z minus 1. So I have substituted the series for z minus 1, 1 by z minus 1, and then 23 by 7. So that is why I have substituted this 20 by 42 and this series. So simple problem. So that gives this series expansion in the given region. So of course, as you know, so if we were asked to find a series expansion in a defined region, we would have to, so our series would have been different. So that is one thing. So depending on the region where the series have to be found, the answer for the series changes. But finally, all these series should converge to the same function, which is given here. Okay, so let us now move on to the third problem. So now the actual involved problems begin. So we have to find the points of singularities of this function and identify the which kind of singularities are there, and then find the corresponding residues. Okay. So we are given a function sin z by z square minus cos z by z. So, of course, so these are given like subtraction of two ratios, and of course clearly these both these terms are singular only at z equal to 0, right? Because sin z and cos z are already entire functions, and in both cases denominator vanishes only at z equal to 0. So that is the only point of singularity. So now, of course, since z equal to 0 is a singularity, now we examine what kind of singularity it is. For that, we have to consider a Lorentz series expansion around z equal to 0. So for that purpose, we have to also expand sin z as a Lorentz series or Taylor series around z equal to 0. So for that purpose, it will be useful. So of course you know this representation of sin z as e to the power minus iz minus e to the power iz multiplied by I by 2, and if we use the series expansion for e to the power z, we get this expansion for sin z. So equation number 1. So, and similarly for cos z, we have this expansion 2. Okay, so these are of course familiar series expansions for sin z and cos z. So now we will use these series expansions. Now we will simply substitute these series expansions 1 and 2 into this function fz. So let us now do that. Yeah, just simple substitution. So I have already included this z to the power minus 2 inside this series. Similarly, cos z by z gives us this series. So simple substitution, and now simple algebraic manipulation. There is nothing. I think these two lines are identical. Oh no, there is one thing. So here in the first, second and third. So in the third line, please note that the summation goes from n equal to 0 to n equal to infinity. But in the fourth line, I have written that the summation goes from n equal to 1 to infinity. Why so? Because as you see, for n equal to 0, this term gives a 0 contribution. So you put n equal to 0 and you get a 0 contribution. And of course, as you know, so 0 factorial is 1. So that is a convention and you can easily relate that. 0 factorial is 1, but if you put n equal to 0 here, you will get a 0. So that is why it doesn't matter if we change the limit of the summation to exclude n equal to 0 point. So now after that, so finally, yeah, so that is the last line. So yeah, so that is the power series. So the power series for this given function around 0, z equal to 0 is this one. Okay, so you see, so you have z to the power 2n minus 1. So if you put n equal to 1 here, what do you get? So you get z. So you see there is no negative power of z. Okay. So the power series in z of fz around the singularity z equal to 0 has no term involving a negative power of z. So as we see here, so that is why z equal to 0 is a removable singularity. So it may seem like, yeah, of course z equal to 0 is a singularity, but it is a removable singularity, because if we assign the value f0 equal to 0, then the singularity is removed. Like if we put z equal to 0 in this series, so what do we have? So we have 0 to the power 1 and 0 to the power 3 and all kinds of these, and all these terms. So of course all these terms are 0 at precisely at z equal to 0. So that is why, so when z is tending to 0, so we have fz tending to 0 also. So that is why precisely at the point z equal to 0, if we assign the value f0 equal to 0, that means the singularity will be then removed. So yeah, that is why z equal to 0 is a removable singularity, and since it's a removable singularity, it has no residue, because residue is the coefficient of the simple pole. So like z to the power minus 1 singularity. So that kind of singularity is absent here, so that is why there is no residue. So yeah, that is that. So we have singularity at z equal to 0, and that is a removable singularity, and hence there is no residue. So that is the answer. So if there is any question, please feel free to ask, because now I will have to move on to the most involved problem of this session. Well, if not, then yeah, let me move on to the next one. So the problem is similar. The problem statement is similar except the function. So the function is now z by 1 minus e to the power z sin z. And we have to locate and classify the singularities and also find the corresponding residues. So how do we locate the singularities? So of course here again, so it is given as a ratio of two functions. So the numerator, that is an entire function, and the denominator, so if we look at this denominator, it has some zeros, right? So the denominator is 0 at these points. So and at the locations of zeros of the denominator, this function will definitely be singular, because and because z is the numerator is already an entire function. So the zeros of the denominator is given by this. So z equal to k pi. So yeah, the denominator is factorized. Okay. Yeah. So the denominator is already factorized, and so of course we will find zeros by considering zeros of these two factors separately. So first let us look at sin z. So when is sin z 0? So sin z is 0 when z is equal to k pi. Of course, and k is an integer. So it doesn't matter positive or negative or 0, but for any integer, a sin k pi is 0. Okay. And what about the other factor? The other one is 1 minus e to the power z. So e to the power z minus 1 is 0 when z is equal to 2 pi I k. See? So that is why the denominator has infinite number of zeros. So like 1 0 for each one of these k. So these are these zeros of the denominator. Now as a side step, we note that the numerator is 0 also only at z equal to 0. Okay. So since the denominator is 0 at these positions, so that is why fz is singular at z equal to k pi and z equals to 2 pi I k for any k belong to z. So yeah, please note that z equal to 0 is also included in this set, right? Because put k equal to 0 and you will get z equal to 0, and that is the position of 0 of the numerator is also included in the points of singularities of fz. Okay, so now what to do? So let us first look at the singularity at z equal to 0. So we'll have to examine this singularity very carefully because as we have seen, the numerator is also 0 here. So at this point, the function is of 0 by 0 form. So we have to be careful, because in the real analysis case, we usually employ the L'Hospital rule to find that kind of limit, 0 by 0 form. So here, let us first look at this z equal to 0, and of course, as you know, so around z equal to 0, our exponential function has this power series expansion, so expansion 3. So this is quite well known. So now we'll substitute this power series into this function fj. So exactly similar like the problem before. So just substitute the power series of e to the power z, and here I have also substituted the power series for sine z. So the power series of sine z, so that was this one, so expansion 1. So here I have explicitly written these terms. So like you have seen that this expansion only contains the the odd powers of z. So that is why I have written these things explicitly. So this is the series expansion of 1 minus e to the power z, and this is the expansion for sine z. Okay, and I have taken z common from both of these factors. So that is, and there was a z in the numerator. So these factors get cancelled, and then we are left with minus 1 by z. Okay, and the minus comes from this first factor. Okay. So now this first factor is written like this one. So 1 plus z by 2 factorial z squared plus 3 factorial and to the power minus 1. So these dots represent higher order terms, and similarly from this second factor I have written it like this. So again z was taken outside, so that is why we are left with 1 minus z squared by 3 factorial plus higher order terms. So yeah, one thing is that to look at the nature of the singularity and to find the residues, we look for negative powers of z. Okay, and we have to keep in mind that we are expanding around z equal to 0. So what do we see? So these two functions, so these two factors, 1 plus z by 2 factorial. So okay, no. Well, so we already have 1 by z factor outside, but if you see, so you will get no negative power of z from these two factors, because so if we simply use the binomial expansion, so what do we get? We get 1 minus z by 2 factorial plus higher order terms, so like ordered z squared terms and higher. And from the second factor also 1 plus z squared plus 3 factorial and then order 4 terms. So you see, you will get no negative power of z from these two factors. And to comment on the nature of a singularity, we have to look at the negative powers of the power series that has been centered around that point of singularity. So here we already know that the maximum negative power can be 1. So now I have also suppressed the higher order powers, and we are left with minus 1 by z plus half plus higher order terms that is not problematic at z equal to 0. So you see, so the negative power is 1 by z. So that is why z equal to 0 is a simple pole of this function. Okay, and clearly, so you see the coefficient is -1, so that is why the residue here is -1. So yeah, in conclusion, z equal to 0 is a simple pole with residue -1. So that was one analysis. Then let us move on to the other singularities. So now we'll examine the singularity at z equals to 2 pi ik for k integer other than 0. So 0 had to be treated separately. So these are the singularities. So now we have to look at this singularity. Here I have used a shortcut. So z by sine z, as you see, it is regular at these points. So it is regular at z equal to 2 pi ik. Okay, and at z equal to 2 pi ik, z by sine z take this value 2 pi k divided by sine h 2 pi k. So this is a shortcut, but yeah, I'll comment later on the applicability of this shortcut. So to proceed further, we also note that e to the power z is equal to e to the power z plus 2 pi ik, because yeah, this second factor gives 1. So this is kind of what you say, periodicity property in the complex plane. So around z equal to 2 pi ik, so when we are saying we have to expand around z equal to 2 pi ik, we have to expand that as a power series of z minus 2 pi ik. Oh, sorry, there is a typo. It should have been z minus 2 pi ik. Yeah. Just okay. So that is a propagating error. Yeah, in all these expansions, so we have to replace this plus sign with minus sign. Sorry about that. So okay, anyway, so we are actually expanding around z equal to z equal to minus 2 pi ik. So then this series is valid. Okay, so around z equal to minus 2 pi ik, so we have this series. Okay, because as you know, e to the power z is an entire function. Thus we have the power series expansion of fz around z equal to minus 2 pi ik, of course for k not equal to 0, so like this one. Okay, so now simply as we have seen before, so precisely at this point z equal to 2 pi ik, this value is 2 pi k divided by sin h 2 pi k. And okay, there is no mistake here, because this 2 pi k divided by sin h 2 pi k, this is an even function, so it doesn't matter if I put k or minus k, the answer remains the same. Okay, and then yeah, so I have substituted the value for z by sin z, and then I am expanding this 1 by e to the power z around this point z equal to minus 2 pi ik. Okay, so I have directly written the series expansion. So this is the series expansion to the power -1. So just substitute this one, and we have to subtract it from 1, and you will get this series, and with power to the power -1. Okay, and then again I have factored out z plus 2 pi ik, and what remains is this. So 1 plus z plus 2 pi ik plus z plus 2 pi ik square plus higher order terms to the power -1, and then I have directly used. So please look at this analysis. So this is exactly similar. So nothing mysterious happening. So I have just jumped several steps. You will understand quite clearly if you get your hands dirty. So let us use this binomial expansion with negative power, and then we will get this thing. So uh, negative power of z, so the maximum negative power is 1, then minus half plus higher order terms. So these O expansion, this includes all the positive powers of z plus 2 pi ik. Okay, so we see we again have negative power of order 1, and its coefficient is given by this. So at z equal to minus 2 pi ik for k not equal to 0, so this is a simple pole of this function with residue this one. So because this is the coefficient of the first order pole. Okay, so in conclusion, so all these points z equal to 2 pi ik are simple poles. So yeah, and then we are left with the last kind of singularities, so that is z equal to k pi. So this is quite, these kind of problems are quite time taking. Okay, so then let us move on to the last kind of singularities. So we examine the singularities z equal to pi k for again k not equal to 0. So clearly z by 1 minus e to the power z is regular, and we simply substitute its value at these points pi k, so which is this one. So please also note that there is this okay, this is kind of anti-periodicity property of sin z. So of course this is familiar from real calculus. Okay, so sin z. So now we will expand around. Okay, again there is a mistake, so it should have been z equal to minus pi k. So again around z equal to minus pi k or k not equal to 0, we have this thing. So sin z is minus to the power k sin z plus pi k. This follows from this periodicity property, and then we will simply use the series expansion for sin z plus pi k. So series expansion is 1. So let us have a look. So this was the series expansion, but here we have to replace z by z plus pi k. Yeah, by z plus pi k. Okay, so this is the series expansion, and then again we have to, so with this power series at our disposal, we now find the power series expansion of fz around this point z equal to pi k. Okay, so we just substitute this value for this z by 1 by e to the power z factor. Okay, and then substitute this series. So that was 1 by sin z, right? So because that was 1 by sin z, so that is why there is this minus 1 power, and then again jumping several steps, so that gives us the final answer. So again this is 1 by z plus pi k plus positive order terms. So like there is no terms with power z with no power 0. Okay, so this is the series expansion with the negative power 1 and positive power starting from plus 1. So there is no terms with power 0. Okay, so since the negative power is maximally 1, so z equal to pi k is again a simple pole with these residues. Yeah, so all of these poles, all of those three kinds of poles were simple poles but with of course different residues. So yeah, that concludes this problem. So I hope it is clear, but of course the best thing to understand these kind of problems is to do it yourself. But yeah, these are the steps that have to be taken. Okay, enough with this series expansions. Now we move on to the problems that involve complex integration using the residue formula or otherwise Laurent expansion. Okay, first let us look at this problem. So we have to find this contour integral around the positively oriented contour. So this is our circle centered around z equal to 0 and radius 3 and positively oriented, and this is our integrand. So of course, so what do we need to do? So to evaluate the complex contour integrals, we need to extract the points of singularities of the integrand, right? So here we immediately see that z equal to 2 and z equal to 1 are the 2 points of singularities of this integrand. And remarkably, both of these points of singularities lie inside the region bounded by the contour, so which is the circle of radius 3, and both these points lie inside this region. Okay, so by now, so we are experienced enough to immediately recognize that z equal to 2 is a simple pole. Okay, and at z equal to 2 the numerator is analytic. Okay, and of course it's a simple pole, and now the numerator has a new kind of singularity. So we have not encountered that kind of singularity in previous sessions. So let us look at that. The numerator is analytic everywhere except at z equal to 1, because at z equal to 1 it is e to the power 1 by 0, and that is divergent. So to extract the property of the singularity, we have to consider a Laurent expansion around that point of singularity. So around z equal to 1, so we have this Laurent expansion. So that is the series for e to the power x and x replaced by 1 by z minus 1. Clear? And that is valid for mod z minus 1 greater than 0. So this series expansion is valid everywhere except precisely at that point of singularity. Okay, so and please look, please understand that so z minus 1 has only negative powers in this expansion. Okay, and so only the negative order poles going up to the infinite order. So since this Laurent series does not terminate at the finite ordered pole but extends toward the infinite ordered pole, so that is why z equal to 1 is called an essential singularity. Okay, so in other words, essential singularity is an infinite ordered pole. So yeah, z equal to 1 is an essential singularity. Moreover, it lies inside the region bounded by the circle. That is why both these points of singularities at z equal to 1 and z equal to 2 will contribute to the integral. Okay, so let us now move on to actually calculate the integral. So yeah, that was the integrand here, and then I have used the series expansion for e to the power 1 by z minus 1. Okay, this is this step, and then in this step I have just removed the summation outside the integral, because yeah, you can interchange summations with integrals, there is no problem. Now, oh sorry, there is another typo. uh, this summation, so this summation should not be there. Sorry about that. Okay, and then so now, yeah, so if we look at this, so this is nothing but the new denominator is constant and numerator is factorized as two polynomials. So clearly this denominator has poles at it has zeros at 2 and 1, and thus this integrand has poles at z equal to 2 and z equal to 1. Moreover, z equal to 2 is a simple pole of this integrand, and z equal to 1 is an nth ordered pole of this integrand. Okay, so simple pole is evaluated simply, so that is why. So for z equal to 2, we can simply use the Cauchy integral formula. So that is what I have used here. And for the higher order poles at z equal to 1, we have to use the higher order Cauchy integral formula. Okay, that involves this differentiations and all that. So another thing we should note that, so this series expansion involves n equal to 0 up to infinity, right? So at n equal to 0, the term has no singularity at z equal to 1. See, and the integrand will have singularity at z equal to 1 starting from the term at n equal to 1. So that is why I have changed the limit of the summation here. So it is changed from 0 to 1 because, as I said, the n equal to 0 term will not have any singularity at z equal to 1. It will have singularity only at z equal to 2. That is why this term is included in this, but not here. Okay, and here we use the higher order Cauchy integral formula. So I have just blindly used the formula and then putting those values and evaluating these differentiations, we are led to this summation. So 2 pi I divided by n factorial minus same, but please note that the summation, the limit of the summations are different. So since there is no n equal to 0 term, but all the other terms get cancelled with each other, and only the n equal to 0 term survives, and that gives us 2 pi I. So yeah, that is the answer to this problem. So yeah, for the first time we encountered essential singularity in this problem. Okay, so we did not actually use the residue formula, but we only used the higher order Cauchy integral formula and all that. Now in the final problem of this session, we will use the residue formula for integrations. Okay, so again we have to do the integral along the positively oriented contour mod z equal to pi of this function. So our integrand is cot pi z. Okay, so yeah, you see that we cannot immediately tell what are the what kind of singularities this function poses, right? Because it is not factorized. So for this kind of problems, it is useful to use the residue integral formula. Okay. Now let us first find out the problems of points of singularities of this integrand, and then of course, as we do usually, so we then check which of these points of singularities lie inside the contour. Okay, so cot pi z, as we all know, is the ratio of cos pi z and sin pi z. of course. And the numerator cos pi z, it is an entire function, so no problem with that. And the denominator sin pi z, it is also an entire function, but it has some zeros. Okay, and clearly the integrand will be singular when the denominator is 0. So that means at the points where sin pi z is 0, this whole integrand cot pi z will be singular. Okay, so sin pi z is 0 when z is an integer. So okay, we have seen this previously, and it occurs here also. So when z is an integer, sin pi z is 0, and we find, and now we will find the residue at the point z equal to k through the Laurent expansion of the integrand. Okay, so residue. So to find the residue, we have to consider the Laurent expansion and then extract the coefficient of the simple pole. So cot pi z, so this is written like this, and of course this is a result familiar to all of us. So cot pi z is equal to cot pi z plus k, where k is an integer. So of course we can write it like that. Okay, again there is a mistake, it should have been z equal to minus k. So we are actually doing a Laurent expansion around z equal to minus k. Okay. And again simply I have substituted the series for cos z and sin z with z replaced by pi z plus k. I have just simply substituted the series in the numerator and denominator, and then yeah, so this is our series, and in this second term I have written this series, all the terms of the series explicitly, like yeah, if we write term by term, you will get this. Okay, and again, so this is the numerator, this first factor. So in the numerator we have 1 minus terms that is at least of the order z plus k whole square. So I have not explicitly written those terms, but in the denominator we have so again I have factored out pi z plus pi k, and then I have written this factor like this. So yeah, so 3 becomes 2, 5 becomes 4, all these things. So I have factored out pi z plus pi k, and this is at in the denominator, that is why there is a to the power minus 1. Okay, then again as we have done in our problem 4, so again repeating that same analysis, we get the series as this. So 1 by pi 1 plus z plus k, 1 by z plus k plus order z plus k. See, again there is no negative power of order greater than 1. So our negative power is of order 1. So that is why this z equal to minus k is again a simple pole. Okay. Thus z equal to minus k is a simple pole, and it has residue 1 by pi. So we see that our residue does not depend on the value of k. So this is same for all integral values of k. Okay, so we just found the residues at the points of singularities of this function cot pi z, and this is 1 by pi. Now to evaluate the integral, so we have to find which points of singularity lie inside the contour. The contour is mod z equal to pi, and we know the value of pi is 3.14, right? So it is greater than 3 but less than 4, and our points of singularities are z equal to integer. So the points which will lie inside the contour are z equal to 0, plus minus 1, plus minus 2, plus minus 3, but not plus minus 4 because pi is less than 4. Okay, so we have 7 points of singularity that lie inside that contour. And what did we just see? We see that uh, all the residues of all the points of singularities are equal, and that is 1 by pi. So now by the residue theorem of integral, we simply write this. So 2 pi I, that is the factor, this is the residue, and this is the number of singularities. And since all the residues are same, we have just written 1 by pi multiplied by 7, and that gives us 14i.